Stand on a scale tonight before you go to bed. Write the number down. Now set your alarm. Get up in the morning. Don't eat. Don't drink. Don't even go to the bathroom. Just walk straight to the scale. You'll be lighter. Not by a little bit, by a pound. Maybe 2. Sometimes close to 3. Where did it go? You were lying there, under a blanket, not moving, not exercising, doing absolutely nothing by any reasonable definition of doing. And yet, mass left your body. Actual, physical, weigh it on a scale mass just vanished from you while you slept. I want to know where it went. Not a vague answer, not you burned calories. Calories are a unit of energy. They don't weigh anything. They don't show up on a scale. I want to trace mass, atom by atom. What specific substance left your body, through which exit, in what chemical form, and where is it right now, this morning, as you stand on that scale? Because if a pound of anything left you during the night, it has to be somewhere. It didn't wink out of existence. Physics doesn't allow that. It's conservation of mass is not a suggestion. It's the law. So that pound is in the room, or it left the room, and I want to find it. This turns out to be a much stranger question than you'd think, and the real answer reveals something deep about what you are. All right, let's investigate. Let's be real detectives about this. Start with the most obvious suspects. You sweat at night. Everyone knows this. You wake up, maybe the sheets are a little damp, your pillow's warm, and if the room was hot, you're properly sticky. So maybe that's the whole story. You sweated out a pound or 2 of water. Done. Mystery solved. Let's go have breakfast. Except, hold on, let's check that. How much do you actually sweat in your sleep? On a cool night, in a comfortable room, maybe 70 degrees Fahrenheit, the answer is roughly 100 to 200 grams. That's less than half a pound. On a hot night, sure, it's more. But people who sleep in perfectly climate-controlled rooms where they barely sweat at all still lose weight overnight. The same pound, pound and a half, so sweat is a contributor, a minor one, but it's not our culprit. It's the guy who was in the neighborhood but didn't commit the crime. What about the bathroom? Well, think about this carefully. I said weigh yourself before you go to the bathroom. Before, and the weight is already gone. Whatever was going to leave through that exit is still in your body when you stand on the scale, so the bathroom didn't do it either. Cross that off. Some people suggest insensible water loss. That's a real thing. Your skin isn't a waterproof seal. It's permeable. Water molecules constantly drift through it, evaporating off the surface. You don't feel it, you can't see it, but it's measurable. And over 8 hours it adds up to perhaps 100, maybe 150 grams. Real mass, leaving through your skin without you sweating at all. Good. That's another piece. But it still doesn't account for everything. Think, if you add up the sweat and the skin evaporation, you're still missing a big chunk. Something else is carrying mass out of your body all night long, and nobody thinks about it. Here's where the investigation takes a turn, and I love this part because the answer is right under your nose. Literally. It's been there every second of your life. You're breathing. Now you might say, of course I'm breathing. What does that have to do with losing weight? And that reaction is exactly why this is such a good puzzle. Because when people think about breathing, they think about oxygen going in and carbon dioxide going out, and they treat it like an exchange, like you're trading one gas for another, and the net effect is roughly nothing. But it's not nothing, it's not an even trade. The air you exhale is heavier than the air you inhale. Every single breath, there's a net export of mass from your body. And over thousands of breaths through the night, that tiny difference per breath accumulates into something substantial. Let me make this very precise. You breathe in air that's roughly 78% nitrogen, about 21% oxygen, and a tiny sliver of carbon dioxide, around 0.04%. Your body takes some of that oxygen and uses it. The nitrogen you mostly ignore. It goes in and comes back out unchanged. But the air you exhale now contains about 4 to 5% carbon dioxide. That's 100 times more carbon dioxide than you breathed in. Where did all that carbon dioxide come from? It didn't come from the air. The air barely had any. It came from inside you. Your body manufactured it. Your cells took carbon atoms that were part of your body, combined them with the oxygen you inhaled, and produced carbon dioxide as waste. And then your lungs threw it out of you, into the room, gone. Think about what that means. Carbon atoms that were physically part of your flesh, locked into molecules of fat or sugar or glycogen, are now floating around your bedroom as invisible gas. By morning, some of them have drifted out under the door, down the hallway, maybe out an open window. Pieces of you, actual atomic pieces, scattered into the atmosphere while you dreamed. That's not a metaphor. That's conservation of mass, working exactly as it should. But let me go deeper, because the chemistry here is gorgeous, and I think it deserves a proper look. What actually happens when your body burns fat? People throw that word around, burn, like it's a figure of speech. It's not. It's very nearly literal. A fat molecule is a real physical structure. You can draw it. It's a long backbone of carbon atoms, 15, 16, 17 of them in a chain, with hydrogen atoms attached along the sides, and a little group of oxygen atoms at one end. That's what fat looks like at the molecular level. It's a thing. It has mass. It has a shape. If you could hold one in your hand, it would be a tiny, greasy, flexible rod. Your body stores billions and billions of these rods. They're packed into fat cells, which is why fat tissue feels soft and squishy. It's basically a warehouse full of these molecular fuel rods, sitting there waiting to be called up when you need energy. And while you sleep, the call comes. Your cells need fuel. They send chemical signals. The fat cells open up, release some of these molecules into the bloodstream, and they get delivered to cells throughout your body. Then the real work starts. When your body metabolizes that molecule, here's what happens step by step. Enzymes in your cells crack it apart. The long carbon chain gets snipped into 2 carbon fragments. Each fragment enters a cycle of chemical reactions, and at each stage carbon atoms get stripped off and paired with oxygen. 1 carbon plus 2 oxygens gives you 1 molecule of carbon dioxide. The hydrogen atoms get paired with oxygen too, 2 hydrogens plus 1 oxygen, and that gives you water. And in the rearranging of all these chemical bonds, energy is released. That's the energy your cells use to do everything cells do. Contract muscles, fire neurons, build proteins, maintain the delicate electrochemical gradients that keep you alive. Now, if you're skeptical, and you should be, you might say, come on, how much carbon dioxide can one sleeping person really produce? It can't be that much. A breath is tiny. Fair enough. Let's do the arithmetic. Because the wonderful thing about physics is you don't have to take anyone's word for it. You can check. So the equation, if you want to think of it that way, is straightforward. Fat plus oxygen gives you carbon dioxide, water, and energy. That's it. Nothing mysterious. Nothing vague. A molecule gets dismantled. Its atoms get reshuffled into smaller molecules. Those smaller molecules leave your body as gas and vapor, and you get a little lighter. Now let me give you a feel for the scale of this, because the numbers surprised me when I first worked them out. You take roughly 12 to 20 breaths per minute while you sleep. Let's call it 15. Each breath moves about half a liter of air. In each exhaled breath, about 4 to 5% is carbon dioxide. That wasn't there before. So each breath exports roughly 20 to 25 milliliters of carbon dioxide. That's a small amount, but do the multiplication. 15 breaths a minute times 60 minutes times 8 hours. That's 7,200 breaths in a single night's sleep, each one carrying away a little puff of carbon dioxide. When you total it up, you exhale roughly 150 to 200 liters of carbon dioxide over the course of one night. The carbon in that gas weighs somewhere around 70 to 90 grams. Add in the weight of the oxygen atoms bonded to that carbon, and the total mass of carbon dioxide you breathed out is roughly 200 to 300 grams. Close to half a pound just from breathing, just from lying there. And that's not counting the water vapor. Every breath you exhale is warm and saturated with moisture. Your lungs are wet on the inside, lined with a thin film of fluid, and the air passing over them picks up water molecules. Think of it like wind blowing across a lake on a warm day. The air picks up moisture whether you ask it to or not. It's just physics. Warm air holds more water than cool air, and the air in your lungs is at body temperature about 98.6 degrees Fahrenheit, which is quite warm. So you inhale cool, relatively dry air, and you exhale warm, humid air. Every single breath. And the difference in moisture content between those two streams means you're losing water mass with every cycle. Over 8 hours, that's another 100 grams or so of water leaving through your breath alone. You can actually see this if the conditions are right. On a cold winter morning, if your bedroom is chilly enough, you can watch your own breath fog. That little cloud hanging in the air, That's water mass leaving your body, little clouds of you dissolving into the room. And here's a detail most people miss. Some of that water wasn't just passively evaporated from your lungs. When your body burns fat, the hydrogen atoms in the fat combine with oxygen to form brand new water molecules. Water that didn't exist before. Your body manufactured it as a byproduct. So some of the moisture leaving you overnight was literally created by the destruction of your own fat. The fat produced carbon dioxide and water, and both left you as gas. So now tally it up. Carbon dioxide from breathing, the big one, maybe 250 grams. Water vapor from breathing, another 100 grams. Insensible water loss through the skin, another 100 grams or so. A little sweat. And you're right in the range, 1 to 2 pounds. There's your missing mass. Case closed. Or is it? Because I can already hear someone in the back of the room saying, all right, fine, I buy the chemistry. But you haven't explained where the mass really goes. I mean, when fat burns, it releases energy. And energy has no weight. So isn't the mass really becoming energy? This is a terrific objection. And it's wrong. But it's wrong in a way that teaches you something important about one of the most famous equations in physics. When someone says they're burning fat or losing weight, what do most people picture? I think they imagine the fat sort of converts into energy, and the energy dissipates as heat, and the mass just, evaporates into nothingness. Some people even invoke Einstein. Well, E equals mc squared, so the mass became energy. As if your body is running a tiny nuclear reactor under the blankets. That's wrong. Satisfyingly, specifically wrong. And it's worth understanding why. Because it touches on one of the most commonly misapplied equations in all of physics. Yes, E equals mc squared is a real equation. And it really does tell you that mass and energy are related. But look at that c squared term. The speed of light is about 300 million meters per second. Square that and you get a number so large it barely fits in your head. 9 times 10 to the 16th. What that means, practically, is that a tiny speck of mass contains a stupendous amount of energy. Conversely, to lose even a microscopic amount of mass through energy conversion, you'd need to release a nuclear bomb's worth of energy. Your body is not doing that. Your body releases maybe 70 or 80 watts of thermal power while you sleep. That's like a dim light bulb. The mass equivalent of a night's worth of body heat, running the equation backward, is something like a billionth of a gram. There is no instrument on Earth sensitive enough to detect that. It exists in principle and is meaningless in practice. So forget the Einstein explanation. It's technically present but physically irrelevant. The mass doesn't leave as energy. It leaves as stuff, as actual molecules with weight you could measure on a kitchen scale. Carbon dioxide you can trap in a balloon. Water vapor you can condense on a cold window. Real substances with real mass that you could, if you were very patient, capture and weigh. People have done exactly that. In metabolic research since the late 1800s, scientists have built sealed chambers, whole rooms, really, designed to capture everything. You put a person inside, you seal every opening, and you measure with excruciating precision every molecule going in and every molecule coming out. Every breath catalogued, every drop of sweat collected, every watt of heat measured through the walls. The instruments are sensitive enough to detect a few grams of difference over 24 hours. And the mass balance is perfect, down to the gram. What the person loses in body weight equals the mass of the carbon dioxide, water, and trace outputs they produced. Nothing missing, nothing mysterious, no mass unaccounted for. It all left through known exits in known chemical forms. This goes all the way back to Antoine Lavoisier. Around 1783, he and Pierre-Simon Laplace designed one of the most elegant experiments in the history of science. They built what they called an ice calorimeter. Picture a container nested inside a larger container with ice packed between the two walls. You put a guinea pig inside the inner container, seal it up, and wait. The guinea pig sits there. It breathes. It generates body heat. That heat melts some of the ice. You measure exactly how much ice melted, and from that you can calculate exactly how much heat the animal produced. Meanwhile, you're also capturing the air the guinea pig breathes out and measuring the carbon dioxide. And here's the knockout result. The heat produced by the guinea pig matched almost exactly the heat you'd predict from burning the same amount of carbon in a furnace. The animal's body was doing the same thing as a fire, combining carbon with oxygen, releasing energy, producing carbon dioxide. Same reaction, same arithmetic. Same atoms reshuffling into the same products. Lavoisier understood immediately what this meant, and it electrified him. Life is not exempt from physics. There's no special vital force, no soul stuff, no mysterious substance generating animal warmth. An animal is a chemical engine. A sophisticated one, yes. A beautifully regulated one. But an engine, all the same. It takes in fuel, combines it with oxygen, produces carbon dioxide and heat, and the books balance. Every gram accounted for. They cut his head off during the revolution a decade later, which was a tragedy for many reasons, not least because the man was one of the finest experimental minds of his century. But the insight survived, and it applies to you right now. You lying in your bed at 3 a.m. are a slow-burning candle. Not as bright, not as hot, but atom for atom, bond for bond, it's the same process. Carbon finds oxygen, carbon dioxide drifts away, water drifts away, the candle gets a little shorter, you get a little lighter. Let me take this one step further, because there's a beautiful circularity here that connects your bedroom to the entire living world, and I don't want to leave without showing it to you. Where did the carbon in your fat come from? Trace it backwards. You ate food. Maybe bread, maybe rice, maybe a piece of chicken. If it was bread, the carbon came from wheat. The wheat got its carbon from the air. Think about that for a second. A wheat plant standing in a field, swaying in the breeze, is literally building itself out of air. It pulls carbon dioxide from the atmosphere, uses energy from sunlight to crack that molecule apart, keeps the carbon, and releases the oxygen. Then it stitches those carbon atoms into glucose, into starch, into cellulose, solid material. You can hold it in your hand. And it was gas a week ago. That's photosynthesis. It's the reverse of what your body does. Your body takes solid carbon-based molecules and turns them into carbon dioxide gas. Plants take carbon dioxide gas and turn it into solid carbon-based molecules. Two halves of the same cycle running in opposite directions, powered by different energy sources. You ate that solid carbon. Your digestive system broke it down. Your body rebuilt some of it into your own structures and stored some of it as fat. And now, at night, you're undoing the whole process. You're breaking that stored carbon back apart, combining it with oxygen again, and breathing it back out as carbon dioxide. You're returning it. The atmosphere lent you some carbon atoms. You held on to them for a while, days, weeks, months, maybe years if they were stored in deep fat reserves. Now you're giving them back, one breath at a time. And somewhere out there, maybe tomorrow, maybe next week, a tree is going to grab one of those exact carbon atoms out of the air and pull it right back into a leaf. That atom might end up in a fruit. Somebody might eat that fruit, and the cycle continues. This has been going on for hundreds of millions of years, long before there were people, long before there were mammals. Every animal that has ever breathed has been doing exactly this, borrowing carbon, returning carbon, inhaling what plants exhale, exhaling what plants inhale. An endless quiet exchange between the living and the atmospheric worlds. Here's what I find so striking about this question. It starts as something trivial, bathroom curiosity. The scale says something different in the morning. A shrug. But if you chase it honestly, if you refuse to accept a vague answer and demand one that works atom by atom, you end up staring straight at the fundamental machinery of life. Conservation of mass, thermodynamics, combustion chemistry, the carbon cycle, the deep equivalence between a candle flame, a guinea pig, and a sleeping human being. And you end up seeing yourself differently. Because the logical conclusion of all this is unsettling and beautiful at the same time. You are not a fixed thing. You're not a collection of atoms that stays put. You're a pattern that atoms flow through. Like a river. A river has a shape, a location, a name. You can point to it on a map. But the water in it is different from one hour to the next. But no molecule of water stays in the Mississippi for very long. But it enters from rain and tributaries, flows through and leaves at the delta. Yet the river persists. It has continuity, it has identity. Not because it holds on to its substance, but because it holds on to its form. You're the same way. The carbon in your body today is not the carbon that was there a year ago. Most of it has been swapped out, breathed out, excreted, replaced by new atoms from new food. Researchers have tracked this with isotope labeling. They tag specific atoms in your diet and watch them enter your tissues, and then weeks or months later leave. The turnover is relentless. Your skeleton takes about 10 years to fully replace its minerals. Your fat tissue turns over in a few months. your gut lining, a few days. You persist as a form, as an organization, as a set of instructions written in DNA that keeps rebuilding you out of whatever atoms happen to be available. But the material, the actual physical stuff is just passing through. Sleep makes this especially vivid because the input side shuts off. You stop eating, you stop drinking. For 8 hours nothing comes in, but the output side doesn't care. It keeps running at full capacity. Your brain alone uses about 20% of your resting energy, and the brain does not take the night off. It's busy all night, consolidating memories, running housekeeping operations on your neurons, processing the day. Your heart beats roughly 60 times a minute all night. Your lungs cycle air in and out, never stopping. Your immune system keeps patrolling. Your cells keep dividing, keep repairing damaged DNA. All of it costs energy. All of that energy comes from dismantling molecules and exporting their atoms as gas. 8 hours of output, 0 input. The scale registers the deficit. One more number just to leave you with a sense of the throughput. If you lose roughly 1.5 pounds per night, and you sleep 365 nights a year, that's over 500 pounds of material passing through you and leaving annually. More than 3 times your entire body weight in exhaled gas and evaporated water every year. And you never notice because it's all invisible. No smoke, no ash, no residue. The candle burns perfectly clean. So tonight when you lie down, try this. Just notice your breathing for a minute. Feel the air come in through your nose. Feel it go back out. And know that each exhale is carrying away a little piece of you. Carbon atoms that were part of your body are now part of the room. By morning, they're part of the sky. And somewhere a leaf is waiting to grab one of them and start the cycle all over again. That's the physics of sleep nobody talks about. Not because it's hidden or difficult, because it's so constant, so quiet, so perfectly ordinary that nobody thinks to ask until you do, and then you can't stop thinking about it. If someone had asked you yesterday, when you lose weight, where does the fat go? What would you have said? I bet it wasn't, I breathe it out. Think about that.